Today, we're diving into a world that's completely invisible, the nanoworld. And that brings up a really interesting challenge, doesn't it? How on earth do you teach someone about something you literally can't see and make it feel real? Well, let's break down how it's done. I mean, this is the fundamental question. It's one thing to learn about planets by looking through a telescope. You can see Jupiter, right? But atoms, molecules, how do you possibly bridge that mind-bending gap between our normal, everyday world and the fundamental building blocks of, well, of everything? So first things first, what even is nanoscience? It's so much more than just making tiny gadgets. The source material calls it a place of disciplinary crossing, which I think is a fantastic way to put it. Picture a giant intersection where physics, chemistry, biology, and engineering all meet. It's in that shared space that we find the basic rules for building everything, from a living cell to a computer chip. Okay, so our first stop on this journey is outside the traditional classroom. We're talking nanoscience for everyone, and how informal science can make this invisible world feel totally real. The number one goal here is to give people a visceral appreciation of scale. Now, that's just a fancy way of saying a gut feeling. It's not about calculating things with a bunch of zeros. It's about intuitively feeling just how mind-bogglingly huge the differences in size actually are. And this idea that scale is delightful is nothing new. We humans have been obsessed with it for centuries. Think about Alice shrinking down to get into Wonderland, or Gulliver waking up surrounded by tiny people. Those stories tap into a core part of our curiosity, and that's the exact same sense of wonder that good nano-education plugs into today. So how do you actually do it? Well, it usually comes down to 3 key strategies. First, you've got visceral scale adventures. These are cool interactive games, a lot of them inspired by that famous film Powers of 10, where you can zoom from the cosmic level all the way down to the atomic. Second, mediated nanomanipulation. This gives you virtual access to amazing tools like electron microscopes, so you can feel what it's like to actually move things around at the nanoscale. And third, you make it personal with local and everyday tales. You show people the nanoworld at work in their phone, their stain-proof pants, or even in research happening in their own town. All right, let's switch gears and head into the classroom. Because here, the whole game changes. We're talking about turning students into nanodetectives and turning the whole class into an investigation. The role of the student just totally flips. You're not a passive learner reading a book anymore. Nope, you're an investigator. You get a case file, a challenge, access to a virtual microscope, and a mission. Figure out what's going on and report back with your findings. And this isn't just aimless fun. It's incredibly structured, just like real science. Students have to follow this rubric. They keep a work log, do the background research, lay out their methods, and present their data. But here's the most important part. They have to interpret that data and acknowledge their own assumptions and the limits of what they found out. This teaches them how to think like a scientist, which is so much more valuable than just memorizing facts. A really big part of this nanodetective training is learning to tell the difference between different types of claims. A scientific assertion, for example, is powerful because it's backed by mountains of evidence and it survived the tough process of peer review. A journalistic assertion is powerful in a totally different way. It's accessible, it reaches tons of people. Knowing the difference between those two is an absolutely vital skill for any citizen today, and these exercises make that crystal clear. Okay, time to level up again. Let's talk about training the next generation of innovators. For students who want to build a career in this field, the training gets way more specific. It's all about honing the skills they'll need for the challenges of tomorrow. And these are some of those key skills. We're talking the real nuts and bolts here. Modeling atom positions, using advanced imaging techniques, processing tons of data, and actually making new nanoparticles. But notice this last two: effective team communication and solving problems from the outside world. The training isn't just technical. It's about being able to work with other people to solve problems that actually matter. Of course, once you get the power to manipulate matter at its most fundamental level, well, that's incredible. But it also forces you to take a step back and ask some really, really important questions. Which brings us right to the ethics of it all. And this isn't just some extra credit assignment, it's taught right alongside the science. Future innovators learn about their responsibilities, stuff like the ethics between labs and their clients, how to handle public research money responsibly, and this is a big one, how to talk about the risks and uncertainties of new technologies in a way that everyone can understand. So, after the games, the detective work, and all the advanced training, what's the ultimate payoff? What's the whole point? Well, it all comes down to building a powerful new way of thinking. Look at this number. 500 million years. That's roughly how long it took the Earth to create all its fossil fuels, and we're on pace to burn through all of it in just a few hundred years. That staggering disconnect in timescales, it shows we have a problem that our usual way of thinking just can't handle. And that is why we need what's called multi-scale thinking. This is the real takeaway here. Learning about nanoscience isn't just about atoms. It's about training our brains to connect the dots between the very, very small and the very, very big, between a tiny action now and its massive consequence later. It's a mindset that is absolutely essential for tackling our biggest challenges, from climate change and sustainability to public health. So, we'll end with a question for you. If you really learn to see the world at this fundamental level, to connect the nanoworld to the world we all live in, what great challenge could you take on? What big problem out there could you solve by learning to think small?